Okay, so we've all interacted with ChatGPT, right? I mean, it's everywhere now.
Absolutely. It's become this go-to tool.
Yeah, for drafting emails, brainstorming, maybe even debugging code. It just feels like it knows things.
It does, and the coherence is often startlingly good.
Exactly. But, for people really interested in AI, the big question isn't just what it does, it's how. How does it actually pull it off? What's really going on under the hood?
That's the million-dollar question, isn't it?
It really is. And today we're going to try and, pull back that curtain a bit. We're diving deep, and our main guide here is Stephen Wolfram's book, What is ChatGPT Doing, and Why Does It Work?
Which is a fantastic resource.
Totally. And the neat thing is, it's actually free online on the Wolfram website. It's about 105 pages, and it hits this sweet spot. Definitely more in depth than a blog post, but not like some super dense AI textbook, really accessible.
Yeah, it's perfect for this kind of exploration. And that's really our mission today, isn't it? To go beyond just listing ChatGPT's features.
Yeah.
We want to explore the underlying mechanics, the bits that are still kind of mysterious, even to the folks who built these things.
That's the wild part.
It is. And we want to look at the bigger picture, too. What does this mean for AI, for how we think about intelligence? This book gives a really unique look into that journey. It highlights how much is still being figured out.
Okay, so let's jump right in because, honestly, this is where it gets really interesting right away. The book hits you with this kind of bombshell. Despite building it, despite training it, we don't fully understand why ChatGPT actually works.
It sounds crazy, but it's true. Think about that.
Yeah.
We've engineered this incredibly capable thing, but the fundamental why behind its success, still a bit of a black box.
It's mind-boggling.
It really is. And Stephen Wolfram himself, he puts it very directly. He says, let me find the quote. Here. It has to be emphasized again that, at least so far as we know, there's no ultimate theoretical reason why anything like this should work.
Wow. So it just...
Pretty much. The book sort of compares it to studying a natural phenomenon. We can observe it, describe what it does, even model its behavior, but that fundamental why is elusive. It kind of challenges how we normally think about engineering, where you usually understand the principles before you build something complex.
Yeah, usually you have the blueprint first.
Exactly. And Sam Bowman, another researcher, he echoes this feeling perfectly. He says something like, we don't really know what they're doing in any deep sense.
Okay.
He goes on, if we open up ChatGPT or a system like it and look inside, you just see millions of numbers flipping around a few hundred times a second, and we just have no idea what any of it means.
Millions of numbers flipping around. That's quite an image.
Isn't it? And he adds, with only the tiniest of exceptions, we can't look inside these things and say, oh, here's what concepts it's using, here's what kind of rules of reasoning it's using. We just don't understand what's going on here. We built it, we trained it, but we don't know what it's doing.
So this massive tool we're all using is fundamentally opaque, even to its creators.
In a deep sense, yes. And that really raises the question, how can something be so powerful, yet so inscrutable? It's honestly one of the most fascinating things about AI right now. It makes you think about the limits of our own understanding, too.
Definitely. So, okay, if we don't fully grasp the why, let's focus on the what. When we strip it all down, what is ChatGPT actually doing? Like at its most basic level, you might think it's some complex reasoning machine.
You might, but it's actually simpler. Surprisingly so, in principle.
On it.
Well, Wolfram explains that its main job, its core task, is just to produce a reasonable continuation of whatever text you give it.
A reasonable continuation, like autocomplete on steroids?
Kind of, yeah. But much, much more sophisticated, obviously. It's not doing deep logical deduction like a human might. Wolfram puts it like this. And the remarkable thing is that when ChatGPT does something like write an essay, what's essentially doing is just asking over and over again, given the text so far, what should the next word be?
Yeah.
And each time adding a word.
So it's just predicting the next word sequentially.
That's the fundamental operation. Imagine you type a word, it predicts the most likely next word, you accept it, then based on those two words, it predicts the third, and so on. Word by word, building sentences, paragraphs, essays.
Wow. Okay, that sounds simple, but the results are obviously not simple. So how does it pick that next word? Does it just pick the single most statistically likely one?
Well, that's where it gets interesting again. You could do that. Just always pick the absolute highest probability word.
Seems logical.
It does. But the book points out that if you do, the text becomes, quote, very flat and boring.
Flat and boring? How so?
It tends to repeat itself a lot, gets stuck in loops, lacks any, flair or creativity. It always takes the most predictable path, the safest bet statistically.
Okay, so that wouldn't produce the kind of varied, interesting text we actually see.
Exactly.
Yeah.
And this brings us to a really key concept, temperature.
Temperature, like heat.
Sort of an analogy, yeah. It's a setting, a parameter you can adjust. It basically controls how risky or adventurous the model is in picking the next word. Okay, explain that. So a low temperature, close to zero, means it will mostly pick the highest probability words. Very conservative, very deterministic, predictable, flat text.
Right, the boring stuff.
Pretty much.
Yeah.
But as you increase the temperature, say towards 0.8 or 1.0, you allow the model to sometimes pick words that aren't the absolute top choice, maybe the second, third, or even 10th most likely word, but still plausible.
Ah, so it introduces some randomness, some variety.
Exactly. It allows it to explore less common paths, make slightly more surprising connections. It's like dialing up the creativity. The book mentions that a temperature around zero point 0.8 seems to be a sweet spot for writing essays. Gives you coherence, but also some interesting variation.
That's fascinating. You often see that temperature setting in AI tools, don't you?
You do. And it makes a huge difference to the output style.
Yeah, the book actually has some great examples using emails, right, to show the effect.
It does, yeah. Imagine asking it to write a follow-up email about an invoice. At a really low temperature, maybe 0.2 or something, it's super formal. Like, I am writing to follow up on the status of invoice, hashtag 12345. We kindly request that you review this matter. Very precise, maybe a bit repetitive, almost robotic.
Stiff, okay.
Then you bump it up to a moderate temperature, maybe 0 0.6, 0.7. It gets friendlier, more natural, but still professional. Something like, I'm reaching out to check on the status of invoice, hashtag 12345. Just wanted to make sure everything is in order. It feels more human, right?
Yeah, definitely more like something I'd actually write.
And then crank it up to a high temperature, like 0.8 or higher. You get much more casual, conversational, maybe even. A client named Hope All's Well just wanted to touch base regarding invoice, hashtag 12345. Much more informal, like a quick note.
Wow. So that one parameter dramatically changes the whole tone and style. It's not just a next word, it's the right kind of next word for the context.
Precisely. It adds that layer of nuance and control over the output.
Okay, so it's predicting the next word with some controlled randomness via temperature, but how does it get so good at knowing the probabilities in the first place? Predicting the right word in English or any language seems incredibly complex. There must be a massive engine under
Well, absolutely. It's not just random guessing. The core technology, the big idea, is what's called a large language model, an LLM.
LLM, we hear that term a lot.
We do. And the goal of an LLM is to estimate the probability of sequences of words, not just memorizing sentences it's seen, but figuring out the likelihood of combinations it's never encountered before. It learns the patterns, the grammar, the relationships, the sort of texture of language.
And how does it learn that?
Through neural networks. That's the heart of it. These are huge, complex computational structures inspired loosely by the brain with layers of interconnected processing units or neurons.
Right.
And you train these networks on just unbelievable amounts of text. Billions and billions of words from the internet, books, articles, you name it.
So it learns by example.
Exactly. Wolfram uses a good analogy. Training a net to tell cats from dogs. You don't write explicit rules like, if it has whiskers and pointy ears, it's a cat.
Yeah.
You just show it thousands of pictures labeled cat and thousands labeled dog.
And it figures out the patterns itself.
It figures out the distinguishing features implicitly. Same with language. You show ChatGPT massive amounts of text, and it learns the statistical patterns, the rules of language, all by itself, just by processing that data.
And the scale you mentioned, it's huge, right? GPT-3, the model behind early ChatGPT, has 175 billion parameters, or weights.
Yeah, 175 billion. These weights are like the tuning knobs of the network. They represent the strength of the connections between the neurons, and they get adjusted during training to make the network better at its task.
That number is just hard to even conceptualize.
It is. And interestingly, a big breakthrough in deep learning around 2011 showed something counterintuitive. Sometimes having more weights, a bigger network, can actually make the training process easier. Finding the best settings for all those billions of knobs can somehow be simpler than with fewer knobs.
That is counterintuitive. More complex structure, simpler training.
In some ways, yeah. It's one of the mysteries they're still unpacking.
And the training itself, how does that work? Does someone have to label all the text?
That's another clever part. It uses unsupervised learning, unlike the cat-dog example where you need labels. ChatGPT learns differently.
How?
You basically just feed it a chunk of text, hide the ending, and ask it to predict the part you hid. The original complete text serves as the correct answer.
Ah, so it learns by playing fill in the blank on a massive scale.
Exactly. As the source says, all one has to do is get a piece of text and mask out the end of it, and then use this as the input to train from, with the output being the complete unmasked piece of text.
Yeah.
No explicit human tagging needed for the core language learning. That makes it incredibly powerful because you can just feed it raw text from the internet.
Got it. And one more clarification, you said words, but the book mentions it doesn't actually work with words exactly. It uses tokens.
Right, good point. It breaks text down into tokens. A token might be a whole common word like the or cat, but it could also be a piece of a word like pre or ing or aeration or even punctuation.
Why do that? Why not just use words?
It helps handle the vastness of vocabulary. It can deal with rare words, technical terms, even made-up words by combining tokens it knows. It also makes the maths a bit more manageable. Internally, each token is just represented by a number, like maybe the is token 914 and cat with the space is 3542. Everything becomes numbers for the network.
So text goes in, gets turned into number tokens. What happens then?
Okay, so roughly 3 stages. First, that sequence of input tokens gets converted into something called an embedding.
An embedding.
Yeah, think of it as a rich numerical representation of each token's meaning and context. It's like a point in a high-dimensional space where similar concepts are close together. It captures nuance.
Okay, so tokens become embeddings.
Second, that embedding gets fed through the layers of the neural network. This is the main computation part, where those 175 billion weights do their work, transforming the information, recognizing patterns based on everything it learned during training.
The number crunching part.
The massive number crunching part. And third, the output of the network is essentially a list of probabilities for all the possible next tokens. There are maybe 50,000 possible tokens it knows.
So it spits out a ranked list. Token X is 30% likely, token Y is 15% likely, and so on.
Exactly. And then, using the temperature setting we discussed, it picks one of those tokens to be the next word, or part of a word, and the whole cycle repeats.
Okay. And all those calculations, those 175 billion operations, that happens for every single token it generates.
Pretty much, yeah. The book notes for each token that's produced, there still have to be 175 billion calculations done. So that, yes, it's not surprising that it can take a while to generate a long piece of text. That's why generating lengthy responses takes time and serious computing power.
Right. It seems instant, but there's immense work happening behind the scenes for each word.
Immense.
Okay, this is super helpful in understanding the mechanics, but the book also goes deeper, doesn't it, into some more philosophical territory. Wolfram talks about this fundamental tension, learnability versus computational irreducibility.
Yes. This is a really profound concept, and it goes way beyond just AI. It's about complex systems in general.
So what's the idea? Learnability and computational irreducibility.
Okay, so learnability is basically about finding patterns, finding regularities in data. It's about compressing information, generalizing, being able to predict things because you found underlying rules or shortcuts. Like learning grammar lets you predict how sentences are formed.
Makes sense. Finding the patterns.
Then there's computational irreducibility. This is the idea that some processes are just inherently complex. You can't predict their outcome or find a shortcut. The only way to know what they'll do is to actually run them, step by step. There are no deeper patterns to exploit for a prediction.
So some things you can learn the rules for, others you just have to simulate.
Exactly. And Wolfram argues there's this fundamental tension between the two. You can't always have both.
How does that play out? Can you give an example?
Think about weather forecasting. That's the classic example the book uses. Meteorologists find patterns, use historical data, build models. That's learnability. They're trying to find the regularities.
Right.
But the atmosphere is fundamentally chaotic. Tiny changes can have huge effects later, the butterfly effect. So predicting the weather accurately, weeks or months in advance, becomes computationally irreducible. You can't just use a simple formula. You essentially have to simulate the entire atmosphere, step by tiny step. And even then, small errors grow.
So you can learn short-term patterns, but long-term prediction is irreducible.
Pretty much. The complexity outruns the learnable patterns.
Okay, that makes sense. Are there other examples?
Oh, tons.
Yeah.
The book mentions financial markets. Traders try to learn patterns from past data, right? That's learnability.
Yeah, technical analysis, algorithm.
But the market is affected by so many unpredictable things. News events, human psychology, global politics. It's ultimately computationally irreducible. No perfect prediction formula exists because the system is too complex and chaotic.
Right. You can find tendencies, but not certain to.
Exactly. Or think about biological systems. Scientists find patterns in genes, pathways, how cells work learnability again. But predicting exactly how a complex disease will progress in one specific person, or every single effect of a new drug, that involves so many interacting factors, it often becomes irreducible. You have to observe or simulate the details.
Even things like urban planning, maybe? Planners use models based on past data.
Good example. They use models learnability, but how a city actually develops depends on countless individual choices, economic shifts, unexpected events.
Hmm.
It's highly unpredictable, irreducible in many ways.
So this tension is everywhere in complex systems.
It really is. And Wolfram connects it back to AI training with this idea of an ultimate trade-off.
A trade-off between what...
He says basically, the more you want a system to make true use of its computational capabilities, the more it's going to show computational irreducibility, and the less it's going to be trainable.
Meaning, if you want AI to do truly complex, unpredictable computation,
It's going to be harder to train it using simple pattern-finding methods. And conversely, the more it's fundamentally trainable, the less it's going to be able to do sophisticated computation.
so if it's really easy to train by finding patterns, it probably can't do that deep, irreducible kind of thinking.
That's the trade-off. Systems good at learning patterns might be limited in their ability to perform truly novel, complex computations that don't follow discoverable rules. It suggests a potential limit to what current training methods can achieve in terms of genuine, creative problem solving that requires stepping outside known patterns.
So what does this mean for using AI like ChatGPT? Does this tension dictate where it shines and where it might always struggle?
I think it does, yeah. It suggests AI will be amazing at tasks where there are learnable patterns, even incredibly complex ones, hidden in vast data.
Hmm.
Language prediction, image recognition, summarizing existing knowledge.
The learnable stuff.
Exactly. But for problems that are fundamentally computationally irreducible, requiring true step-by-step simulation or novel insights beyond pattern matching, it might hit a wall. Deep scientific discovery, maybe, or creating truly unpredictable art, or navigating highly novel situations with no precedent in the training data.
So intelligence isn't just pattern matching and prediction. There's this other element.
There might be, yeah, this irreducible computational aspect. It's a really important point when we think about the future capabilities and limitations of AI.
Absolutely. Now, connected to this, Wolfram makes another interesting point. Despite how amazing ChatGPT feels, he argues computers haven't suddenly become, vastly more powerful in some fundamentally new way.
Right. It's not like there's been a leap in the fundamental limits of computation, like breaking the laws of physics or something.
So what's changed then? Why does it feel so much more powerful?
The argument is that models like ChatGPT are just doing the same kinds of computation computers have always done, but they're doing it much, much more effectively for certain tasks, especially language.
Because of the scale, the training.
Exactly. The scale of the neural network, the massive training data, and the specific architecture allow it to capture the statistical patterns of human language incredibly well. So it's more efficient and effective at that specific kind of pattern matching, but the underlying computational limits haven't vanished. Those computationally irreducible problems, still irreducible.
Okay, so it's a breakthrough in efficiency and application for language tasks, not a change in fundamental computing power.
That's a good way to put it.
Yeah.
The breakthrough is in harnessing existing computational power to mimic human language patterns implicitly, not in creating a new type of computation.
This then leads to another really mind-bending idea from Wolfram about language itself. He suggests the basic answer, I think, is that language is at a fundamental level somehow simpler than it seems.
Yeah, that's a big one. If ChatGPT can learn to generate coherent, meaningful language just by predicting the next token based on statistical patterns,
then maybe the underlying structure of language, the rules that make it work, are actually simpler or more regular than we appreciate.
that's the implication. Maybe the complexity we perceive is just a surface layer, and underneath, there are more fundamental learnable regularities that the neural network is tapping into, even if we don't explicitly know what they are.
Wow. And if that's true, what does it mean?
Well, the really exciting implication is that ChatGPT's success might be hinting at the existence of major new laws of language and effectively laws of thought out there to discover.
Laws of thought, like fundamental rules for how we reason and communicate.
Exactly, the principles that allow us to structure ideas, make connections, understand meaning. Right now in ChatGPT, these laws are implicit. They're buried somewhere in those 175 billion weights, learned from the data,
Hidden in the network.
hidden in the network. But Wolfram's point is, if we could somehow figure out what those laws are explicitly, if we could understand the fundamental rules the AI has implicitly discovered,
We could potentially build AI differently.
yes, we could potentially do the kinds of things ChatGPT does in vastly more direct, efficient, and transparent ways. Instead of this massive, opaque black box, we could build systems based on the explicit principles of language and thought.
That would be huge. More efficient, more understandable AI.
And it wouldn't just revolutionize AI. Discovering explicit laws of thought would also give us profound insights into human cognition itself. How we think, how our language works. It's like ChatGPT is accidentally acting as a giant scientific instrument, probing the structure of human knowledge and expression.
That's an amazing prospect. Uncovering the hidden rules of our own minds by studying these artificial ones. Did the book, or maybe ChatGPT itself, give any examples of what these laws of thought might look like?
It's speculative, of course, but yeah. As a kind of fun test, ChatGPT was asked to suggest some potential laws it might be implicitly using.
What did it come up with?
It suggested three interesting ones. First, a law of conceptual association. This would govern how concepts link together. Why apple makes us think of fruit or red. Why justice connects to fairness.
The network of meaning in our heads.
Exactly. Understanding that explicitly could lead to AI that makes much more relevant connections. Second, it proposed a law of cognitive economy.
Cognitive economy, like
Yeah.
being mentally efficient.
Precisely. How our brains prioritize information, filter noise, focus resources on what's important for the task at hand. Formalizing that could make AI much better at managing complex tasks without getting bogged down.
Okay, that makes sense. What was the third?
The law of semantic generalization. This is about how we take specific examples and generalize to broader concepts. You see one dog, you learn about dogs in general.
From the specific to the universal.
Right. If we could make that process explicit, AI could potentially learn much faster and apply knowledge more broadly from less data. It wouldn't need to see quite so many examples.
So these are hypothetical laws, but they point towards trying to make the implicit workings of these models explicit.
That's the exciting frontier. Moving from these giant implicitly trained models to potentially smaller, more efficient, transparent systems based on explicitly understood principles of language and thought. It's a path towards not just better AI, but deeper self-understanding.
What a journey. So if we try to bring this all together, we started with the mystery, right? We built this thing, ChatGPT, but we don't fully know why it works so well.
Right, that fundamental opacity.
Then we saw its core function is surprisingly simple in a way, just predicting the next statistically plausible token, but using temperature to add variety.
Driven by these massive neural networks trained on unbelievable amounts of text using unsupervised learning the patterns implicitly.
Which brought us to that deeper tension. Learnability, finding patterns versus computational irreducibility, the inherent complexity that can't be shortcut.
A fundamental trade-off that likely limits what AI trained this way can ultimately do, especially regarding truly novel, irreducible computation.
And finally, this idea that maybe language itself has simpler underlying rules, these laws of thought that ChatGPT has implicitly discovered. And the big prize would be making those laws explicit.
Exactly. So if you connect it all, ChatGPT isn't just a cool chatbot or a productivity tool. It's kind of acting like this accidental scientific instrument. It's forcing us to confront deep questions about language, knowledge, computation, and maybe even the nature of intelligence itself. It's revealing things, perhaps, about the structure of thought.
That really leaves you with something to chew on, doesn't it? It makes you think beyond just the tech. If these laws of thought might be discoverable from studying AI, what other fundamental laws might be out there, hidden in plain sight? Laws governing complex systems, maybe even laws governing our own societies or our own creativity, just waiting for the right tool or the right perspective to make them explicit.
That's the big question, isn't it?
Yeah. Diving into how ChatGPT works really forces you to reconsider what understanding even means for us and for machines. It's a fascinating journey.